Hello everyone, my name is Sachin Kathari and today I'll be presenting my fourth lab report titled Lab 4, Rope Physics Spring Mass Lab. The goal of this lab was to examine and understand the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring by combining fundamental principles we have learned, including both the momentum principle and the energy principle, along with Hooke's law or spring force. We will see that the spring mass system does indeed satisfy the energy principle. The momentum principle will be useful in predicting the motion of the object. First thing we did in this lab was obtain position data with tracker from the video that we downloaded offline. We set our calibration stick to be 0.7 meters from the fixed attachment point, which is also our origin, so that means the mass is hanging in the negative y direction. Our point of mass was the mass, and I basically tracked the motion of it as it swung in an arc on the oscillating spring. So we obtained the x and y positions from here, and we get initial position data and the total time from tracker. Our system for this lab was the mass, the spring, and the earth, and I'll explain why it's clear that the earth is included in our system later in my code. As usual, some initial conditions were given to us, and these included the mass as 0.402 kilograms, the initial position which we obtained from tracker, and the initial velocity which was 0. Down here we tell Python to read data from the CSV file that we saved the tracker position data on, so then we can later compare it. In this portion of the code, we set the gravitational constant as we know it to be 9.8 meters per second. We calculated the stiffness of the spring to be 6.83 and the relaxed length of the spring to be 0.123. Right here, Python basically measures the length at every position, which it does by subtracting the position of the ball minus the position of the spring. L hat gives you direction, which is basically a unit vector. And S is the stretch or the compression of the string. If S is greater than 0, you know that the spring is being stretched, and if it's less than 0, then you know the spring is being compressed. So in this portion of the code, we're computing the system energies that we already know we're going to have, which is the kinetic energy, the potential gravitational energy, and the potential spring energy. And the kinetic energy is 1/2 mass times velocity squared. The potential gravitational energy is mass times gravity times the position y, and the potential spring energy is 1/2 ks s squared. Now we get to our while loop. The total time obtained from tracker was found to be 9.307 seconds. Next we define the initial kinetic, gravitational potential, and spring potential energies to be equal to their respective finite energies, but these three values, the k, u, g, and us, are going to be updated, which we'll see later in the code. Here we calculate the interactions or the forces on the objects. So we have gravitational force, we have spring force, which is Hooke's law, which is the stiffness of the spring times the stretch or the compression times the direction it's going in. The next line is F net, which is simply the sum of the gravitational plus the spring. And these two are very familiar to us now. It's the momentum principle and the position update of formula. So the position is going to get updated every time, and a new L will be calculated from the position of the ball minus the position of the spring. L hat will give us direction, as we saw earlier, and S is the stretch or compression of the spring. One thing I do need to mention is that Newton's second law and the position update formula are going to give us new velocities and new positions, which means that these K and UG are going to change because at every new position, a new velocity will be there and a new position will be there for potential gravitational energy. And down here we basically tell Python to graph it, so now let's look at the graph. So let's watch the code run now. So the first thing we should notice is that the blue arrow is the spring force, which is the spring pulling the mass back up, and the black arrow is the gravitational force pulling the object down. The red ball is the position data from the tracker file, and so the mass is trying to follow it, it's trying to stay right on top of it, but the reason why it's not is because human error, round-off error values will always be present, and that is why it doesn't follow it on the dot, because the red dot represents experimental data. So now let's compare the graph, or at least look at it. The blue line represents delta k, the red line represents delta us, the green line represents the gravitational potential, and the sum of all of them is 0. And because the sum of all of them is 0, we know that the energy principle has been satisfied answering the first what does it mean question. Because we know that energy is conserved when we include our surroundings into our system, that the change in energy should be equal to 0. So that answers our first what does it mean question. Because delta K plus delta US plus delta UG is 0, that means that change in energy is 0, which means the energy has been conserved and the energy principle has been satisfied. For the second question, we were supposed to find periods of oscillation first from the x position data and second from the y position data, and then compare the two. So I found the periods of oscillation from the x and the y, and in reality these two should be the same. The time should not change. The time for the object to move left or right should be the same for the object moving up or down. Time isn't a vector quantity that has components. The reason there is a slight variance between these two is because experimental data from tracker cannot be 100% correct. Human and round-off error will always exist in experiments. Well, that was my lab, and I really appreciate you guys watching.